Okay, but the tools to problem solve don't end there. I've said also consider the above statement in terms of complex conjugates. This is where each of two complex numbers having their real parts identical and their imaginary parts of equal magnitude but opposite. So if I go back to this diagram again, you can see the real part. If I get let's get this color here. If I get the real part would be that for these two. I'm comparing these two here, Z2 and Z3. The imaginary part, let's use a little bit of a yellow. That, I didn't recognize I was on that tool. The imaginary part is equal and opposite. So we can call that complex conjugates. Now, given what I've suggested that Z2, this is equal to omega, and then Z cubed is the squaring of that, so it's omega squared. We can also have a conversation about this statement I've written here, that Z cubed is the complex conjugate of Z subscript 3, my mistake. Z subscript 3, is the complex conjugate of Z subscript 2. And we can write that, as I've done very scrappily here, as omega squared equals omega star. And it's not star at all, it's omega complex conjugate. This is the complex conjugate of that. That's the way we represent complex conjugates. And you can see it manifesting itself here. When multiplying out that, this is what you would have obtained. You would have found that you end up with a minus I root 3 over 2, whereas this was a plus I root 3 over 2, and hence they are complex conjugates of each other. Omega squared, which is Z3, is the same as the complex conjugate of the original omega. That is a tool that we can also utilize when solving problems, this one. Also know what occurs when adding these terms. You can consider them like vectors in their own special complex little way. That is to say, here is our 1, there is our 1 there, and there's our Z1. I called it Z0 in the past, I apologize if that was confusing. There's Z1, there is our Z2, that value of this minus a half. So I've gone minus a half in this left direction. Let's get that purple out. I believe purple is what I used before. So in these circumstances, I'm going to go minus a half in this direction. And then I went up by a I root 3 over 2 amount there. That's what's happening there. And note that I can also do the same top to tail as if I'm doing a physics vector S question on forces. Top to tail, I could take this minus a half again. I moved minus a half in this direction there. This is not to scale, of course, and minus root 3 over 2 in the imaginary direction of y, wrong tool, and therefore I would end up with that. Now, in these circumstances, you can see they close off on each other, and this concept would be equivalent in a physics forces conversation as saying the resultant force is 0. And then it's manifesting itself here in that we have our 1. If you take your 1, you plus your omega, which is Z2, your omega squared, which technically is Z3, but we can keep it in this omega form to simplify this down. There's your omega squared. Mathematically, if you add all three of them together, you will get 0. But also notice how it's visually possible to produce a diagram that allows for us to visualize that. And this occurs if it was Z to the power 4, you'd find that with 4 vector-like objects that would close off. 5 would also do the same, 6, and it will carry on in this pattern. They will all close off like forces do for resultant. Like you would utilize a diagram of forces in order to calculate the resultant force to suggest that the resultant was 0 if that were the case. In these circumstances, just to prove what I'm talking about, in case I'm going off topic here, I've just stated it that 1 plus minus a half plus this, these circumstances, minus half is 1, that will cancel out the 1, these will cancel to make 0, so this is just the case anyway, even if you're not comfortable with the diagrammatic form there. Now, let's consider a problem. Let's throw into the problem. Consider the following problem. Find all the solutions to Z cubed equals 1. Now, we've technically gone through that.